Hi everyone, this is Jelle Vos. I'll be presenting an SoK paper that I wrote closer to the start of my PhD in collaboration with my two promoters, Mauro Conti and Zeki Erkin. This work is on multi-party private set intersections, and they're called multi-party because they involve n parties. They're called private because they compute the set intersection without revealing other information. Sets here refers to the set that each party brings to the table, which can contain at most k elements, and the intersection is what we compute. Now we are specifically interested in collusion-resistant MPSIs, and those protocols withstand T colluders. This is a system overview of a typical MPSI protocol. Here n is 3, so there are 3 parties. There's always one party that we designate the leader, and the leader obtains the final output. So let's give all these parties a set. After an MPSI protocol, the leader will get access to the intersection, which contains only elements 1 and 4. Our research goals when we wrote this SoK paper were to provide a high-level overview of MPSI protocols, to analyze how these protocols perform in general, and to identify common pitfalls. This is the outline of today's presentation. The gray parts were not covered in the in-person presentation, but they are covered in this presentation. We first start with the systematization and a small overview of underlying techniques. Then I present 3 takeaways, and to end with common pitfalls and future work. So one of the underlying techniques is a bit set representation. It's a kind of set representation that is very, very simple. It contains a bit for each element in the universe, and it will be set to 1 if the element is in the set, and 0 if not. So if we have 2 sets, we can compute the intersection by computing an AND operation. You can see that the final bit set is exactly the intersection. Now, a bit set is pretty large because it grows with the size of the universal set U. So let's say if you're encoding IP addresses, you'll be storing 2 to the power 32 bits, which is a lot. But if your universe is small, such as for example in veto voting, you can get away with a much smaller bit set, and maybe a bit set representation is very efficient in those cases. A technique that does not suffer from this large space requirement is a Bloom filter. Bloom filters are approximate set data structures. So let's encode the elements 1 and 3 into this Bloom filter. Like a bit set, it's a bit vector that starts off at 0. We insert 1 in this case, and for that we use a few hash functions to select the bits that we're going to set to 1. Now we can also set the bits for 3. If we have multiple sets, we can combine the sets to compute the intersection, again by computing an AND operation. Now in this final Bloom filter, we can not directly extract the elements, but we can by checking, for example, from set 1, which elements are contained in it. And so here you can see that 1 is not contained in the Bloom filter because the final bit is set to 0. But 3 is. Notice that Bloom filters can potentially contain false positives. So if you query it on an element, there is a non-negligible chance that a false positive will occur. A hash set looks a lot like a Bloom filter, but it only has 1 hash function. So we can study it in the same way that we do with Bloom filters, but it is less space efficient. The fourth encoding that I want to discuss is the polynomial roots encoding. It's an encoding where for each element in the input set, we add a root to the polynomial. Polynomial roots are very convenient to work with because they work well under arithmetic. So if we have 2 sets represented as polynomial roots, then, for example, we can query them on the element we like to check and add up the results. If the result is 0, then with high likelihood this element is contained in both sets. If it is not, such as in this case, it is probably not in both sets, or actually for sure it's not in both sets. Our systematization works by grouping together 3 high-level parts of the MPSI protocols. We define private homomorphic set representations as protocols that first somehow aggregate the inputs, then reveal the set representation, and only then query it. A leaky homomorphic set representation is one where we also have to perform queries before revealing. So these queries have to be performed privately using some kind of secure computation technique. And then finally, aggregatable membership queries are protocols that first query all the individual sets, aggregate those membership queries, and then reveal them. Now, we think that these 3 high-level constructions cover all the possible constructions, because if we aggregate after revealing, then we risk leaking information about the individual sets. Now let's give 3 examples of possible set representations that can be used for each of these high-level constructions. Bit sets are examples of private homomorphic set representations, because the final set representation is actually exactly the set representation representing the intersection. So given the intersection, if we encode it, we get exactly the same representation. So we can just reveal it completely and do querying offline. Now, Bloom filters are examples of leaky homomorphic set representations. But when they are aggregated, they are not exactly the representation of the intersection. If they were, then this one on the left would not exist. So Bloom filters are examples of leaky homomorphic set representations, and that is why people also perform queries under encryption and only reveal the output of the query. Now, polynomial roots can be used as aggregatable membership queries. And so we would only actually reveal the output of these queries. Our first takeaway is that real-world parameters for MPSI protocols are not yet known. So there are dozens of MPSI protocols out there, but no practical deployments. And one reason why there are so many MPSI papers is that it is very easy to just take any set representation and any secure computation technique, and out comes a possible MPSI protocol. However, to choose which one is the right one, we would need to know what real-world parameters look like. So there are still many variables for which we do not know how to actually set them. What is clear is that of all the MPSI protocols that have been proposed so far, there is none that actually is the best in every single case. So it is specific to each set of variables whether a protocol is the best one or not. So here is a grand overview of a couple of the important variables. So completely on the right hand side, you can tell what are like MPSI specific variables. But for example, the number of threads and the CPU, so the hardware that you use, but also the network that you have, so the network latency and network throughput, also all count towards the final completion time. Some protocols perform better with a very high number of threads, while others also perform quite well with a low number of threads. So it is not always easy to compare existing MPSI protocols. Now, takeaway 2 is that old insights are still relevant, and these insights aren't even that old, but there are plenty of recent papers that do not take into account these older works. So one example is the work by Cheon et al., which uses a polynomial roots encoding as a private homomorphic set representation. Then there is the work by Bay et al., which uses Bloom filters, and the work by Haze et al., which again uses the polynomial roots encoding, but this time as an aggregatable membership query. So what all these works have in common is that they rely on additively homomorphic encryption. What we have done in our work is instantiated all of them with the same additively homomorphic encryption scheme, specifically elliptic curve-based alchemal. Then we can measure the cost in terms of the number of elliptic curve multiplications. So let's show a table. In this table, we'll denote by the number of we denote T as the number of colluders. There are n parties, and capital E is a measure of the false positive probability, the inverse. So here's the table. You can tell that these works, and so this table represents the number of curve multiplications, and we count cheap multiplications as 0.25. Cheap multiplications are multiplications where you can perform some kind of recomputation ahead of time. So as you can tell, these works all shine in different areas. For example, the work by Bay et al. Requires very few operations on the leader. The work by Haze et al. Requires few operations on the assistant. But if you want to minimize the total complexity, maybe you'd like to go for the work by Jeon et al. Our final takeaway is that protocol description should be sufficiently general, and people have already been busy doing this. One very useful primitive is oblivious key value stores. These are stores that store key value pairs, returning randomness if queried on unknown keys. But if they're queried on a known key, they return exactly the value that was stored in them. A more recent abstract primitive is that of encrypted membership query filters. These filters store sets, returning ciphertext encrypting 0 if queried on elements in the set, and with very high likelihood, they return a non-zero encryption otherwise. One thing we have seen in older works is that they typically follow the following paradigm. They start with a two-party private set intersection, then someone finds out a multi-party extension in the semi-honest model, and then it is extended to the malicious case. However, some papers directly present a malicious MPSI, and this makes analysis significantly harder. It's harder to get the high-level point across. Now, some works use general primitives, such as additively homomorphic encryption, as a closed box, while others use specific instantiations, such as PA encryption. And just as you saw on the previous slide, it is a lot easier to compare if we work with general primitives. Some protocols are even on such a high level that they might be better described using arithmetic circuits instead of a specific secure computation primitive. Now, I finally want to go over a few common pitfalls. One is that sometimes leaky set representations are used as private set representations. One example is that a few works have used Bloom filters but have not performed queries under encryption. So the entire Bloom filter is released at the end of the protocol. This, however, leaks a lot of information about the input sets. Some protocols use unsafe randomness. So if parties work together, they can de-randomize the data used in the protocol. One common mistake, for example, is to let the leader provide randomness, as the leader at some point holds the values for all parties, or the combined values. But just having the leader provide randomness is typically not enough, because if the leader would collude with an assistant, they can obtain information that they couldn't in isolation, and then work together to de-randomize. Also, the randomness should not depend on the sets of the parties that generate it. So sometimes randomness is only included in certain cases. For example, if a specific element exists in the input set. This means that if few parties have a certain element in their set, that the protocol essentially has less secure randomness. Finally, adapting to the malicious model comes with additional challenges, and that is being shown by Abadi et al. That show that the polynomial roots encoding has several fragile points to it, and Q et al., which show an attack where malicious assistants can also learn the intersection. So, as you saw in the beginning, we were studying the case where only the leader obtains the intersection, but in this way, assistants could also obtain the intersection. There is still a lot of work to be done in the MPSI space. Specifically, the most important point is what should real-life application settings be like? Until then, we cannot really perform applied cryptography. We can only think of what are interesting settings and try to design accordingly, but it will remain guessing work. Another question is, can we find a generalization of encrypted membership query filters? EMQFs are already quite general, but they do not cover all topics. They do not cover all primitives that are being used in MPSI schemes. Finally, this brings up a question, can lattice-based MPSI protocols outperform current protocols? There have been so many MPSI protocols, but very few of them are based on lattice-based assumptions. So, just to wrap up, our main takeaway is that real-world parameters for MPSI protocols are not yet known. Secondly, old insights are still relevant and sometimes ignored. And finally, protocol description should be sufficiently general. If possible, we could define even more abstract primitives. Thank you very much.